Okay, so for our next problem, we have on a multiple choice test, problem 1 has 4 possible answers and problem 2 has 3 possible answers. There is only one correct answer. What is the probability of randomly guessing the correct answer to both problems? So what I have here is a matrix with problem 1 and problem 2. In problem 1, let's say we have A, B, C, D as possible answers, and E, F, G as possible answers for problem 2. And let's say that the correct answer for problem 1 is B and the correct answer for problem 2 is G. Well, there's only one way that we can get both of these right, and that's by selecting B and G. Well, if we count out all the cells possible, there's 12 cells, and that means that we have a 1/12th chance of getting that correct answer. Another way of looking at this is if we take the probability of selecting the answer from problem 1, that's a 1/4 chance, and the probability of selecting the correct answer from problem 2 is a 1/3 chance. And then if we multiply those two probabilities together, then we have a 1/12th chance of getting it correct. That's, of course, if we're just randomly guessing. So this next one, we have using a 6-sided die numbered 1 to 6, find the probability of rolling odd numbers 3 times. Well, on a 6-sided die, we have 3 odd numbers, 1, 3, and 5. So we have a 3 out of 6 chance of getting an odd number, which then will reduce to 1/2. So if we multiply 1/2 times 1/2 times 1/2, we end up with a 1/8 chance of rolling odd numbers 3 times. So that's just like Mr. Fulton Bolton, huh? Okay, so a family has had 9 girls in a row. Find the probability of this occurrence. Well, when you have a child, you have a 1/2 chance of having a boy or a girl. And so we would need to multiply 1/2 a total of 9 times. So our probability is just going to be 1/2 to the 9th power, which I believe is 1/512. Hopefully I didn't make a mistake there, but I'm just going to jam to the next one here. We're going to look at dependent events now. We're moving away from independent events. And we have a bag that contains different colored marbles. 3 blue, 2 red, 4 green, and 1 yellow. A marble is chosen at random. Then without replacing it, a second one is chosen at random. Find the probability of pulling a blue marble and then a green marble from the bag. So let's go ahead and start off by finding the probability of pulling a blue marble from the bag first. We have 3 plus 2 plus 4 plus 1 marbles. That means we have a total of 10, and so pulling a blue at first represents a 3 out of 10 chance. Now, we want to pull a green one after that. And the reason why this is a dependent problem is because once we've pulled the blue, there's 1 less marble. And so now we have only 9 marbles in the bag. And so we have let's see, there's 4 green, so we have a 4 out of 9 chance then of getting a green. And if we multiply these two probabilities together, then we have a 12 out of 90 chance there. And 12 out of 90 then will reduce to 6 out of 45. And, oh, we could reduce that more, right? So we have a 2 out of 15 chance there. Alright, let's look at another dependent problem. We have a card is chosen at random from a standard deck of 52 playing cards. Without replacing it, a second card is chosen. What is the probability that the first card chosen is a queen and the second card chosen is a jack? So recall from the previous problems that there are 4 queens within a 52 standard deck of 52 cards, and there's also 4 jacks within a standard deck of 52 cards. So we first have a 4 out of 52 chance of selecting a queen. Now once we've picked that queen, now we only have 51 cards. But we still have the 4 jacks. We have a 4 out of 51 chance of getting that jack. And so we have to multiply these two together and simplify. Let's see. What we get is a 4 out of 663 chance. Alright, let's move on. We're going to look at probability with permutation here. Oregon's lottery game Lotto Mucho is set up so that each player chooses 4 numbers 1 to 20. If the 4 numbers chosen exactly match the 4 numbers in the same order, the player wins the top cash prize. With 1 Lotto Mucho ticket, what is the probability of winning this prize? So we have 4 numbers to choose here from 1 to 20. And the first number that we pick, we have 20 different options, but once we pick that first number, we only have 19 options, and then 18, and then 17 options. So to figure out the total amount of options possible, we have to multiply these together. And we end up getting 116,280. So the probability of actually winning this prize represents a 1 out of 116,280. So just remember that the order matters means that if the winning numbers come out as 3, 20, 17, and 14, we have to exactly match that order with the 3 first, then the 20, and then the 17, and then the 14. That's a permutation. A combination, remember, is when the order doesn't matter. So if this represented a combination problem, we could have picked the 14 first, and then the 3, and then the 20, and then the 17. As long as we get those same numbers, then we would win if this were a combination problem. And why do I bring up combination? Because that's the next problem here. We have Florida's lottery game, Lotto Max, is set up so that each player chooses 6 numbers, 1 to 53. If the 6 numbers chosen match the 6 numbers, the player wins the top cash prize. With 1 Lotto Max ticket, what is the probability of winning this prize? So let's figure out how many different combinations we have. And remember, it's easiest to find a combination by first looking at a permutation. So we have 6 numbers to choose from. And we have 53 numbers actually, but we have 6 spaces available. In the first space we have 53 numbers, and then the second we have 52, and then 51, 50, and 49, and then 48. And so if this were a permutation, we would simply just multiply all these numbers together. But this is not a permutation. Order does not matter in this case. And so what we need to do is we need to divide by the number of ways in which we can arrange those 6 numbers. And that means that we're going to have to divide by 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And I said 3, but I didn't write it. Okay, so we end up with 22,957,480. And our chances of actually winning the prize represent a 1 out of 22,957,480. So remember, if this were a permutation problem, we would have even less of a chance of winning. Alright, let's move on to the next problem. Oh, we have probability of an event not occurring here. The probability that an event E will not occur is equal to 1 minus the probability that it actually will occur. So this one piggybacks off of the previous problem we did with a combination. We have seen that the probability of winning Florida's lotto with one ticket is 1 out of 22,957,480. What is the probability of not winning? Well, we would simply need to subtract the probability from 1. The probability of winning from 1, and that gives us, I'll go ahead and pause it for you. Okay, so there's our probability of actually not winning, right? And let me show you the actual decimal, which converts to 99.99999 Not very likely. Okay, so here I have a problem pretty much done for us. When flipping 3 coins, find the probability of getting at least one head. Well, this is kind of piggybacking off one of the problems we did earlier. Remember flipping 3 coins. We have 2 options, 2 options, 2 options, right? And so there's a total of 8 possibilities. And if we want to figure out the probability of at least one head, well, we have to think about the probability of just getting all tails, because there's no heads with all tails. And the probability of tails, tails, tails is just a 1 out of 8 chance. And so we have to say 1 minus 1 out of 8, and then that would give us the 7 out of 8 chance of at least getting one head. Okay, so I will see you all in class. Hopefully this is enough so that you can get your start with the project.